Okay, okay.
Tyash, first your introductory note.
Okay, so good afternoon, everyone. It is a
Good
great
afternoon.
honor and pleasure to welcome everyone in the today's guest lecture organized by Signal Processing Society Student Branch, IIT Kharagpur. I welcome all the participants here and thank you for showing your interest in today's talk. On behalf of the IEEE Signal Processing Society Student Branch, IIT Kharagpur, I welcome our guest lecturer, Dr. Anirban Chakraborty. We are grateful for him for accepting our invitation as the guest lecturer for today's event. Dr. Anirban Chakraborty is the Associate Professor of University of Engineering and Management, Kolkata. Before joining the college, he was attached with the Electronics and Telecommunication Engineering Department at IIEST Shibpur as a temporary faculty for 2.5 years. He did his PhD in the Department of Electronics and Telecommunication in the same institute, Shibpur, India, in 2020. He obtained ME and BTech from Jadavpur University and Netaji Subhash Engineering College, respectively. His research interests include digital signal and image processing, VLSI logic design, front-end and back-end developments. He has 20 international publications, including one book chapter as well. Today, our guest is going to talk about a few challenges that are associated with hardware accelerated computations. So, without any further delay, I would definitely request him to continue with the session. And I kindly request all the participants to mute themselves and wait patiently for the end of the session. He would definitely be addressing any question that you have in your mind. And please kindly fill up the attendance sheet that would be provided during the course in the chat box. So welcome, sir, and please continue with the
Thank you.
session.
Okay. Can you see my screen? Is it visible? Okay.
Yes, sir, it is.
So today's topic is hardware realization of basic image processing operation and its challenges. So before going to the hardware realization and the necessity of hardware realization or the challenges people face while realize any image processing operation in hardware, before going to all of this, I would like to present some basic imaging operation. Means what kind of imaging operations are there. Nowadays, those basic imaging operations are very rare. Means nowadays, computer vision has encroached into the domain of people's real life domain. But apart from computer vision, some basic imaging operations are there. Like these are the overview naturally you can find. First of all, what is an image? The image is nothing but a matrix. You can see this is matrix. This matrix you can see this image is nothing but the representation of this matrix. If we zoom the image, we can find out each and every pixel. Some pixel are white, some are black. Black means its intensity value is 0, white means its intensity value is 1. So this image, this the letter A is nothing but a matrix of zeros and ones. This is the image. So it is the quantitative aspect of image. Quantitative aspect means there are some positions of 0 and 1. Suppose this 0, it is in the fourth row and third column. So the positional index of this 0 is fourth row, third column. And in that positional index, the intensity value is 0. So the pixel which presents a third row and a fourth row and third column, the pixel intensity is 0, means it is black. So this image can be quantitatively represented by using matrix. Here also one example I have given for quantitative analysis. In the previous image, only zeros and ones are the intensity values, only two level intensity values. Here, the intensity levels are different. You can find out to 170, to 38, 85, 17. Now, lower intensity value means it is a darker. Suppose here this pixel is darker pixel. So here it is low intensity value, 85. This pixel is completely white. it is high intensity value 255. So there are several intensity levels. These are called gray levels. It is called grayscale image. So we have find out so far two kind of image. One image where the intensity levels are 0 and 1, that is binary image. Another image is that where there are several gray levels. Means each of the pixel, the intensity value represents its gray level. Okay. Like this image in this slide, the gray levels are distributed from 0 to 255. Okay. So means if we want to process this image by means of software or hardware, as of now I am talking about software only. If we want to process this image by means of software or hardware, we need to see the image or we need to perceive the image by using this matrix representation. And each pixel has its value, that is intensity or brightness. We need to see this image in that way. And that intensity is distributed from 0 to 255. Means the intensity can be represented by using 8-bit number, 8-bit binary number. Because if we represent the intensity by using 8-bit binary number, we can have 256 level, which can be represented by 0 to 255. Total 256 levels. So it is also called uint 8 representation, means 8-bit integer representation. The image is represented, the intensities or the gray levels of images is represented by 8-bit integer. Here also it is 0 to 255 levels are there, so it is also uint 8 image, and it is the letter 8, which is which I have taken from a very popular dataset, MNIST dataset, which is required for machine learning application. This 8, letter 8 is zoomed here, and each of the pixel, when I zoom the letter, here each of the pixels are segregated. Okay? And each of the pixels have different intensity values. Like I want to show that the image and its matrix representation side by side. Here the image and its matrix representation are overlapped, so that you can easily understand that this pixel is 181, this pixel is 248. So the greater intensity values means the more white is the intensity levels or brightness, and darker pixel means less intensity levels. Okay. Now here I have given another thing. So quantitative aspect of image, there are three things. First of all, spatial coordinates. So each pixel has a coordinates, that is two values x and y, that is row number and column number. Another thing is that for each coordinate there is an intensity value, that is brightness. So three parameters are there to quantitatively represent a image. That is, three parameters means the coordinate value, and in that coordinate a intensity value. Okay. Now that intensity value, suppose this coordinate, the intensity value is 0, or here 1, that is a single value. For each particular coordinate, the intensity level is a single value. This is called single value grayscale. If for a particular position, the intensity level is not a single value, that is multi-value, then it is called color image. I am showing it here. You can see this is a color image. So this is a color image. If we segregate the image, then we can see there are three levels are there: red, green, and blue. This image can be segregated three channels: red channel, green channel, blue channel. So suppose this pixel, this is second row, second column pixel. This pixel, where my cursor is moving, second row, second column. So this pixel has three values. You can see the second row, second column has a red value. The second row, second column has a green value also, and it has a blue value also. So this red value, green value, and blue value, these three together combine by means of a formula to generate this color image. Like in this color image, this small portion, through this small portion, the intensity values are showing here. This is red values, this is green values, and this is blue values. So for each pixel, for each position, suppose this top corner position, you can have three values: 240, 207, 234. So this top corner pixel has red value 240, blue value 207, and green value 234. So what is the challenge here? Yeah, the challenge is complexity is 3 times increased. That is threefold increase in the complexity. If we want to process a color image instead of a grayscale image, and we need to process the three channels separately: red channel, green channel, and blue channel. We need to process these three channels separately, so the processing's computation time, the hardware requirement, and the all the parameters like total time for computation, operating frequency, everything will be affected by this nature, by this threefold increased nature, because here three channels are there. So you can say one color image is equivalent to three grayscale images. Okay. Here also this color image you can see easily perceive that this color image has three channels: red channel, green channel, and blue channel. So we need to process this color image by using processing individual channels. Okay. But there are techniques. Instead of processing three channels separately, we can process the color image directly also. There are techniques. For today's session, I am not going into the deep into that processing, because I have made the slides and everything very basic for image processing part and the hardware challenges part. There is a image to hardware test case or case study, and also how we represent image processing by using hardware. So all these things so far we have discussed constitute the quantitative part of a image. Means its pixel, the intensity level, the position of the pixel, brightness, whether it is darker or brighter, whether it is multi-valued in intensity or a single valued intensity. So all these things are quantitative aspects. Quantitative means there are certain values, numerical values for each pixel position, and the pixel position is also numerical. So if we want to process those numerical values, we can easily do that by using simple mathematical manipulation or mathematical computation, like the contrast. Contrast means the pixel intensity of a pixel and the difference of the pixel intensity of the next pixel. Suppose a pixel is 250 and the next pixel, immediate next pixel in the right side is 85. So there is a more gradient, means the change in intensity value is more. It is called high contrast image. Okay, so all these things, contrast, thing, equalization, everything is quantitative aspects of image or quantitative processing. I am coming to this aspect also, quantitative processing. But there is some qualitative aspects, and ultimately these qualitative aspects matters the more, because whenever a image, it is generally used to perceive or to see by human eye. Suppose a medical image, ultimately it will be analyzed by a doctor's eye. Satellite image, ultimately it will be analyzed by a scientist. So ultimately human eye is the best judge. So human eye does not see a image by using its metric representation. Whenever you see a image, you don't know its metric representation. You don't know the actual pixel intensity. But how you see? From image, the light rays come into our eye and it causes neural excitation and we can perceive. So it is not in this slide, but I would like to say that there are three things. Among the image, there are three things that affects our human eye the most. One is the brightness level that affects the contrast. Easily human eye can perceive the contrast. One is brightness level, another is contrast, and another is luminance. Luminance and brightness both are similar, quite similar, but there is a small difference. Luminance means, suppose brightness means the pixel intensity, but luminance means whether the image glows itself or not. That is called luminance. So all these three things excites human eye. So this is qualitative aspect which matters the more. Like you can see here in this image, if you concentrate on this dot on here, on the middle of the black spot, then you can perceive that the black spot is growing slowly. If you concentrate here, you can perceive the black spot is growing slowly. But actually, if you fixed your focus here or here in the edges, you can find that it is not growing. So whether the black spot is growing or not, thing is that black spot is not growing. Means all the pixel intensity here is fixed. It is not an animated image. pixel intensities are fixed here. But the human perception, if someone focus on this middle of the black spot, he can perceive that the black spot is increasing, it is growing. That is the difference between human perception and intensity level. Okay. So as I have told you, there is a difference, little bit difference between the intensity and luminance. So here intensity of all the pixels are fixed. But if you concentrate in the middle of the dot, or where my cursor is, you can perceive that it is growing because the luminance can change. Luminance will be changed at the edge. When you concentrate here, the luminance of these pixels will be changed periodically because it is periodic in nature. And whenever I is fixed here, and this periodicity is already in human brain, then the luminance of this edge pixel will be changed, though the intensity will not change. That is why there is a feel that the black spot is growing. So there is difference between human perception and the quantitative aspect. Now, the discussion so far, what is the necessity? Means what is the necessity of discussing image in qualitatively as well as quantitatively separately? Because is that quantitative analysis is required everywhere. Means if you want to implement the imaging operation by using Python or C programming or MATLAB, that is software based realization, or if you want to design a dedicated, means a digital circuit that can process the image, everywhere it is used quantitative. Means everywhere image is utilized by using pixel intensity. There is no luminance, no chrominance, only intensity. That is a fixed value for grayscale image or 3 values for color image, but that is a fixed, that is fixed. But human eye perceive it by using luminance and chrominance. Luminance is somewhat similar to intensity and chrominance is the color. So there is a difference. If you want to process the image by using hardware or software, it will be quantitative analysis, but ultimately the output will be analyzed qualitatively. So it is difficult. That is why image processing task is difficult. You have designed the image processing very perfectly, but quantitatively. Means the image is perfect, there is no noise, perfectly the contrast is matched, but still it may arise that the visual quality of the image deteriorates. That is the challenge of the image processing engineer. Now there are types of image. Binary image I have told you before, where each of the pixel can be represented by using 0 or 1. Here you can see in the cat, here these white dots are 1 and the black are 0. Grayscale image are not only 2 levels, there are several levels, darker, more brighter, and this is a color image where there are 3 values of a particular position, okay, red, green and blue. Now how the red, green and blue are combined, this is image conversion. Suppose this cards, this picture in the left hand side is color image and it is gray image. How we convert this left image to this right image, means how we convert color image to gray image. There are several equations, but this is the most popular image, 0.3 into red value plus 0.59 into green value and 0.11 into blue value. If we combine these 3 red, green and blue intensity in this way by using this equation, we will get the grayscale intensity of this particular position. That is the most popular formula. Even I have also utilized this formula in my PhD task when I want to design from image, color image to grayscale image. But for why I have utilized this formula? Because there are in MATLAB, also in Python, there are dedicated functions. In MATLAB, the function is RGB, means red, green, blue, RGB to gray. If we write RGB to gray, within bracket, the RGB image path, then it will result into a gray image. It will already converted. It will be converted by this function, RGB to gray. Similar kind of functions are also available for Python. But I have done this because in my PhD, I have worked with a multidimensional analysis. I will come to that point with later. I have considered these 3 values RGB by 3 vectors, and combination is a single vector. And I have gone to geometric algebra, means this formula is converted into geometric algebraic representation so that the 3 coordinates can be combined into a single coordinate very easily. by using compact mathematical equation. Anyway, from grayscale to binary image, that is very easier by using thresholding. Thresholding means suppose I have designed a threshold, suppose 100. If the pixel intensity is greater than 100, suppose this position, this dot, if the pixel intensity is suppose 85, it is less than 100, so it will be black. Here you can see it is black. Suppose this pixel intensity, it is 105, so it is more than 100, so it becomes 1, that is green, white. So if the pixel intensities are greater than 100, it will be 1. It is less than 100, it will be 0, that is black. So all the pixel intensities are divided by using two numbers, that is either white or black, the 0 or 1. That is called thresholding. This thresholding is also utilized in case of neural network also. You can easily, you know that in neural network also for multi-class or analysis, the pixel intensity, not pixel intensity, the features are segregated by using threshold value, by using threshold function. So I will come to that point later. Now, another basic image processing task is histogram. So we have discussed the image conversion. Next is histogram. Histogram analysis. Histogram analysis means, suppose this is a image. This image is called cameraman, and this cameraman image, suppose here in the right hand side graph, you can find there are certain values 0, 50, 100, 150, 200, 250. Means these are the intensity levels, and this is in the y coordinate, there are number of pixels. So 0 to, suppose here you can tell it is a 30. So from 0 to 30, the image pixel intensity, because between 0 to 30, this kind of image pixels are up to 3000 in this picture. 3000 pixels are such where the intensity level is 0 to 30, and from 30 to 100, the pixel number is very less than 500. There are very less number of pixels in this image. In this image, there are very less number of pixels having intensity levels 30 to 100. Again, the image, there are very great number of pixels between 150 and 200. There are 150 and 200. There are more number of pixels. So it is a representation of the intensity levels and number of pixels in that intensity level. What is the necessity? You can easily see here the shirt of this man is black, so very less intensity, that is darker. So, and this shirt is long, so the darker pixel intensity will be, the pixels which with darker intensity will be more, which is represented by this 0 to 30 intensity. The pixel number is more than 3000. And also there are several white kind of things, this water, these things. So from 150 to 200 also there are more number of pixels. So it is a representation of the several intensity level. Means for a particular intensity level, whether it may be 64, 74, for a particular intensity levels, how many pixels are there. So what is the utility of this image histogram? You can find out by using contrast enhancer. Here you can see it is a retina picture of eye. It is a retina picture where these are the veins of the retina, and these veins here the veins are not easily segregated from this, because here it is darker. So here the vein and the trajectory of the vein cannot be understood by the doctor, because here the black background and the vein are mixed up, so you cannot understand. But here in this picture, it is more or less the veins are clear, and here the veins are absolutely clear in this figure. The veins, all the veins and its trajectory are absolutely clear. So whenever a doctor analyze a retina picture, then this kind of contrast enhancement will be of much use. And how we achieve this contrast enhancement? By using this histogram. By using this histogram equalization. How? Here you can see there are more dark pixels here. Up to this, almost darker. Up to this, almost darker. So dark pixels are more here. And then the white pixels are very less. So if we equalize means by using linear equalization, means all the pixel intensity and number of pixel positions are linearly varying. So this histogram, the pixel intensity are linearly varying here. Means we deliberately distributes the pixel intensity or gray levels. then we have got this. But if we utilize non-linear pixel representation, means all the pixel intensities are non-linearly distributed, means lower pixel are less, then non-linearly it will vary towards the higher number of higher pixel intensities. So lower pixel intensities and higher pixel intensities are varying in this by following this curve. If we do that, we have got a Gaussian curve. Okay? Gaussian curve of the histogram, almost similar to Gaussian, not Gaussian, almost similar to Gaussian curve. That is natural distribution, means the grayscale levels are naturally distributed over the whole image. So as the grayscale level are naturally distributed over the whole image, so this darker portion is distributed all over the image, and this portion is not darker now, and we can easily perceive the vein trajectory. So that is a contrast enhancement we can achieve by means of histogram equalization. So that is the utility of simple image processing task. It is. Another simple image processing task is dilation and erosion. Dilation and erosion means suppose this test. Okay, we have written the test, and here we can see each of the test is bold. It is bold enough. T is bold, E is bold, and here it is thinner. It is eroded. So eroded means thinner, dilated means bold. Suppose this is the original image, this is eroded image, means thinner, and this is again dilated image. So what is the utility of these three? First of all, sometimes we require the thinner image to segregate each and every portion very clearly. Then we go for erosion. Sometimes we require very dilated image. Suppose this test is not visible from a long distance. This eroded test is not visible from a long distance. So if this kind of image is there, then we have to dilate the image to make it visible from a longer distance. Okay. Suppose a dilated image is there, like this, a dilated image. Then all these portions are connected. You can see all these portions are connected, and we cannot easily see what is written or what is there. Then erosion will give you a full picture. So dilation and erosion are performed by using a structural element. Means a structural element means a 3x3 matrix element. That is called structural element. This 3x3 matrix element is applied all over the image, and then it becomes dilated. Erosion is similar kind of thing. It is basically called morphological operation. Means nothing but OR operation, XOR operation in this way. These are basic operations. Now sharpening and smoothing filter, you can see here, this is very blurred. This image is blurred. This image is sharp. So from blurred to sharp image, we can achieve by applying this filter, this kind of filter. And from this sharp image to blur image, we can apply this filter. This filter is averaging filter. Okay. This filter is averaging. Why? Because when we apply this filter, anyway, suppose here we apply this filter. So all the pixels, 1, 1, 1 means all the pixels will be multiplied with this kernel, and it will be added. After that, it will be divided by 9. There are 9 pixels. So 9 pixel intensities will be added, and it will be divided by 9 to get a single intensity here. Means all the intensity levels are averaged. So if we average all the intensity levels, then the finer details will be lost. We have averaged everything. So averaged means finer details is lost. So we will get a blur image. Now, if it is blur image and we have done in this way, so what is the difference? Here, this pixel will be multiplied by -1, and then central pixel will be multiplied by 9. So central pixel will be enhanced, and the rest of the pixel will be degraded, and then we will add up all these things, and we will put in the middle. So still the middle pixel and the surrounding pixel will be, that intensity difference will be more, because the surrounding pixel are multiplied by -1 and middle pixel is multiplied by 9. So difference is more. Though we have added up all these things, central pixel and the side pixel, and then we put the added up value in the position of the central pixel, still the surrounding pixel and the center pixel, the difference is more. Pixel intensity difference is more means it is high contrast image. It's easily, like you can see here, these lines, these white lines, this black line and white line, if the intensity of this black background and this white lines, if the intensity difference is not much, then we cannot easily perceive these white lines in the black background. You can see here also white lines are there. Here also white lines are there, but it is not as clearly visible as here. Because here the pixel intensity of this white line and the chin of the tiger, the intensity level are more or less same. So there is sharpening and smoothing. These two kinds of things, sharpening and smoothing, are also utilized in several places, specifically in medical images, satellite images. Okay. So there are several applications. Means sharpening application, you can easily understand that suppose brain MRI or lungs MRI. Then the tissues, soft tissues or small tissues, and larger tissues. The difference between the tissues are understood by using their intensity levels. So if the intensity levels vary much, then you can easily understand the tissues separately. So you have a full complete picture if the tissues are highly contrasted. So you use sharpening filter there in case of medical images. And why we require blurring images or smoothing images? Suppose in certain application we don't require such segregation or something. We only require a very gross picture. Then we average all the pixels. A very gross picture we need it sometimes with the with very efficient storage. Because whenever an image is blurred, its resolution is less, then the image size will be reduced. Now this is how a filter is applied over an image. Suppose this is a filter. This is a filter. It is applied over here, this green position. So all these things, 40 into 0, plus 42 into 1, plus 46 into 0. All these things will be multiplied. 46 into 0, 50 into 0. All these things will be multiplied, then added. Then this added value will be positioned in the center pixel. That is, in place of 50, it is written 42. After that, this filter is applied here. After that, this filter is applied here. In this way, for each row, we will shift the filter. We will multiply the filter kernel coefficient with the image pixels, and we will add up, and we will position the pixel or the added up value in the center pixel. That is the application of filter over image. This is the noise of image. This is called salt and pepper noise. This noise can be removed by using averaging, as I told you. Several other methods are there in spatial domain. Averaging is the most utilized method. So this is the noisy image and this is the cleared image. So noise can be cleared by using several basic imaging operations. This is also noise, but this kind of noise cannot be cleared by spatial domain operation. For removing this kind of noise, we need to go for spectral domain. Spectral means Fourier transform. All of you know Fourier transform. Suppose this image is a spatial signal. It is not temporal signal. There is no concept of time. In case of still images, there is spatial coordinates or spatial position of a particular pixel. So it is a spatial domain signal and two-dimensional because each pixel position has two coordinates. So if we Fourier transform, that is 2D Fourier transform this image, we will get this kind of spectrum. This spectrum, you can see here the frequency varies and here the amplitude of that frequency. So you can see this is the low frequency region and this outer layer is the high frequency region. Low frequency region carries a great number of pixel values. You can see a great amount of energy is concentrated within this low pixel position, a low frequency position. So what is basically low frequency position? Low frequency position bears the gross information about the image. Gross information means it does not bear the information about the gradient of one pixel intensity to the next pixel intensity. It does not bear the information. It only bears the gross information, like the shape of the image, the average pixel intensity of the image. Okay, size, shape and size of the image or object or average pixel intensity, all these things are called gross information or the average information of the image. This average information is born by this low frequency region, and when we go for high frequency region, the finer details like the contrast, gradient, average gradient, all these things appear. So here you can see this noise is such that noise is periodic, and when there is noise, you can see this is the white strip, this is black strip. So there is a great pixel intensity difference between one white strip, one black strip. There is a great pixel intensity difference. So it is, we can say it is a high frequency component. Means this noise is a high frequency component. So indeed, these dots appear because of here these dots, high frequency outer layer dots appears because of this noise. So if we, in the frequency domain, if we put this high frequency components 0, like this here, this is black dots, means this high frequency component we have put 0, then you can see the noise is removed. Here more high frequency components are removed, noise is more removed. Here also more high frequency components are removed, noise is removed. But you can see here the contrast and here the contrast. Here it is a blur image. Here though it is noisy, but it is a clear image. So when we remove the high frequency components, so along with the noise, some image details like image contrast also removed. Okay. So in an image, there are low frequency, high frequency component, and each has several significance, separate significance. Like the low frequency component tells us about the image, shape, size, average pixel intensity, and high frequency component tells us about the contrast, the gradient of the image. Okay. So actually contrast enhancement means providing more and more high frequency components. Okay. Means when we apply sharpening filter, if after applying sharpening filter, if we perform Fourier transform of the sharp image, then the high frequency component of that image will be more. Okay. So if we apply blurring or smoothing filter, and if we convert it into Fourier domain, then the high frequency component will be removed. That is the difference. So it is all the things I have discussed is the basics of image processing. Now we will come to the challenges and all these things. Before that, a fun kind of thing, like here you can see it is an Einstein picture. Okay. Now it is an Einstein picture. Now if we made it very small, can you see Einstein? It is the picture of Marilyn Monroe, but blur. You can see the picture is Marilyn Monroe picture, but in a blur way. If you see, this is a Marilyn Monroe, but in a blur way. But when we increase it, it will be Einstein picture. So what is actually happened here? The two picture, one is Marilyn Monroe, another is Einstein. We have mixed up by using frequency. Means the low frequency of Marilyn Monroe picture is added with the high frequency component of Einstein picture. So when we zoom the image, our eye perceives the high frequency component, means the contrast, the gradient of intensity, all these things are highly perceived by our eye. Apart from the shape and size of the image, the finer details are more and more taken by our eye. Then we can perceive it as a Einstein picture. But when this figure is shortened, is when we zoom out the figure, then our eye perceives it as an average thing. Means our eye cannot perceive great details. Just averagely we can perceive the image. Then Marilyn Monroe figure appears. That is the difference. Means our eye is also sensitive to low frequency and high frequency component. When we see some figure from a long distance, then the average of that figure, means the average shape and size is perceived by eye. When we zoom in a figure, then our eye can perceive along with the low frequency, the high frequency content also. Okay. So this is the interrelation between the quantitative and qualitative analysis. Now I will show you some thing. Now see, those are the basics operation of image. Now there are some advanced image operation like image registration and image fusion. Recently I was doing, and in my PhD also I have done work in image registration and image fusion, that is called image information enhancement. So what is that image registration and image fusion, and why hardware is required in that domain, and why challenges are there in that domain? So I will explain the challenges of designing a imaging algorithm in terms of hardware and the necessities by using this domain, this particular domain. Okay, but all the discussion are applicable to other domain also, like the other computer vision domain, image segmentation, object identification. Those are computer vision domain. all these domains, the same discussion is also applicable. I will also sum up all these things later. First of all, image registration means you can see it is a SAR, synthetic aperture radius, and it is a grayscale image. And it is a ETM, means enhanced thematic mapping. Thematic mapping means here several themes are there. Some portions are green, some portions are red. Red means they are the habitats or habitation or human house. Human habitation is more, so it is red. Green means there are lands, means the lands of agriculture. And this deep green or black, this portion, deep green or black means water body. Okay, so it is thematic mapping. Means by utilizing the color, we can segregate between different types of things in a image, where the habitats are there, which one is a agricultural land, all these things. So this thematic mapping is also got from the Landsat 7, means a satellite image, and this SAR image where the thematic mapping are not there, but the exact position of a house or exact position of the water body is perceived. Means this grayscale image is utilized for determining the exact position of a body like house or water body or agricultural land, the exact position. And here thematic mapping is utilized not for determining the exact position. We cannot determine the exact position of the habitat by using this color image. Only thing is that we can determine how much portion of this image is occupied by habitats, how much portion of this image is occupied by water body. Okay, so these two figures have separate utilities. This thematic mapping has separate utilities. This SAR image also has separate utilities. So if we want to know the total amount of habitat along with its exact position, the total amount of water body or exact shape of the water body along with the position it occupies in the whole area. In the whole area, the area occupied by the water body can be easily seen by using thematic mapping. But its exact position, or whether a office or house is just beside the water body, this position can be perceived by using this SAR image. So if we overlap these two images, then we can get two kinds of information easily. So how we overlap? You can see here the water body is zoomed, here it is not. Okay, here it is straight and it is somewhat tilted. This SAR image is somewhat tilted. So what we can do, we have to first register these two images. Means that we have to match the coordinates of these two images. The image registration means matching the coordinates with a reference frame. Matching the coordinates of the both the image with a reference frame so that both the images are aligned. This alignment, image alignment is image registration. After the alignment, so for aligning both this image, this SAR image, we have tilted the SAR image. You can see this SAR image is a bit tilted here. Then we can overlap these two images. Here we have overlapped these two images, and then we can get the exact information of the position as well as the proportion. Position as well as the proportion can be easily seen by this fused image. So image registration and image fusion together enhance the information because we can get more information. So together this process enhance the information. So this image registration and image fusion, basically the image registration are utilized for the front end or for the pre-processing step of a handful of imaging tasks. It may be computer vision also. Suppose image segmentation. In case of certain image segmentation also, 3D image segmentation, first of all, we need to register. So image registration can also be used as a pre-processing step of image segmentation also. Object identification also. So this image registration and image fusion, both of these techniques are highly utilized in case of image processing field. So we have decided in our PhD to do the thing. Here another example where you can easily perceive. Here there are 5 images. In the top row, there are 5 images. And none of the images give you the actual information. Here you can see 2 bins, 2 dustbin, and 1 corridor. Here the corridor is taken but from different angle. Here another corridor is taken. Here another figure. Here also another figure. Means all the images are taken and all the images gives you the information but segregate. But if we align all these images, means all these images are aligned here, we can get the information that it is a bilane or it is a corridor, L-shaped corridor. Here the actual position of dustbin is this, and here the entry is this. So all the information can be get by registering all the small images. So the utility, medical imaging and satellite imaging, we need not to capture this huge image or the clear image. We need not to capture clear image at all. We can capture low resolution image and from different angle, and then we can register all these images. Then we can get the actual information. So suppose the brain MRI, we can take picture of the brain from different angles, from different position, from different time. After that, when we register all these images, we can easily perceive the growth of tumor. If the images are taken at different time and registered, then we can easily perceive the growth of tumor. If the brain MRI are taken from different angle and then registered, then we can have the total 3D volumetric brain idea. The idea about total 3D volumetric brain. Okay. So image registration is medical imaging and satellite imaging, biometric imaging also, everywhere it is required. All the applications of image registration and image fusion are given here. But the main thing is that the real-time processing is sometimes required. Mainly in medical imaging, real-time processing is required for guided surgery. When the surgery is performed by using robotic hand, then suppose there are 5 cameras are set up along with the human body. Over the human body, 5 or more cameras, generally not 5, some 10 or 12 cameras are set up all over the body, human body, and a robot performs the surgery. That is called guided surgery, and this robot is guided by a computer. How it is guided? From information of all these 12 cameras, all the informations are fused. Then a highly informative content is generated, which is fed to the robot, and the robot can easily apply the surgery. So for guided surgery, this real-time image registration is required, because if all the camera takes picture and we register the pictures taken at a different point of time or very slowly, okay, then the information will be fed up to the robot sometimes later. Then it is not going to be a successful surgery, because then and then the picture is taken, the image need to be fused then and then with the difference of milliseconds, and it needs to be fed to the robotic hand in a millisecond. If we want to perform all these tasks, image registration and image fusion, in a millisecond, with high operating speed, then by using GPU, by using CPU, it is possible. By using GPU, if you increase the core and if you utilize the core, there are several techniques to utilize the core more and more. If you do that, it is possible, but it is costly. No one can tell you that GPU are not costly. GPU are costly. If you want to go for more sophisticated GPU, more cost need to be there. Even nowadays, the GPUs are invented for a very high speed operation, very high speed. Okay. So what is the need for hardware? A very high speed achieving of a very high speed by using GPU incurs you high cost as well as high power consumption. Means recurring cost as well as installation or setup cost together, both are more. So if you want to do that in a cost effective way in this hard world country like India, you need to go for dedicated hardware. Means there should be a chip, but the only functionality will be to fuse or register the images and send the output to the robotic hand. Then it can do that by using in a millisecond accurately. Okay. So the term costly is important here, costly and power hungry, because it is not the case that such kind of things cannot be implemented by using software. Real-time things or real-time operation can be made in software efficiently, even more efficiently than hardware, because software are flexible. Hardware, if you generate a chip, it is not flexible, but its cost is more, and in India, it matters the more, or it matters a lot. So we need to design a hardware for image registration and image fusion, but what is the problem or who restricts that? huge computational load. Image registration and image fusion, several computations are there, not only addition or multiplication. Several complicated operations are there. And in multidimensional 3D image, multidimensional operations are there. So if we map the algorithm to hardware, it will be a very bulky hardware. So first of all, we need to overcome the computational load that hurdle, then we can design the hardware. So the necessity of hardware is cost effective and power efficient. And the challenges is that when you want to map a algorithm to hardware, you need to see the computational load of the algorithm. If the computational load of the algorithm is more, the hardware is going to be complex. So first of all, you need to convert the algorithm into hardware realizable. After that, you can convert it into hardware. So I want to show you one of my work, that is Cortex-based image registration. So quickly, I want to show you. My time is running out. There are two images of MRI. This is the reference image. This is the floating image. Or we need to overlap this image or register this image with this. That is a very simple application we have taken. So here we have taken one ground node. Here ground node. We have joined that by using a line, and it is a specific feature, means a specific intensity or a specific gradient. We have chosen this node, and this particular node is here in this picture. This is called feature extraction. We have utilized the features, and all the features are mapped. This is called feature mapping. These features are mapped, and it is joined by a straight line. Now what we need to do, we need to overlap this vector, this A vector, with this C vector, so that this figure is overlapped with this figure. Okay. This figure will be overlapped with this figure when this A vector is overlapped with C vector. Okay. So you can see, when this A vector is overlapped with this B vector, and this C vector is overlapped with this D vector. Okay, because this B vector and this A vector are similar, but rotated. A vector is rotated with respect to B vector. So we need to rotate it again to make this A vector aligned with this B vector. And this rotation, you know, the Cortex is a very hardware efficient algorithm for rotation, vector rotation. So this image, this whole image, we have considered by using some vectors. How we get the vectors? By joining a datum node or ground node with the features. By using datum node and ground node, we get the vectors and the corresponding vectors in the reference image. And those vectors we need to overlap by using Cortex-based vector rotation. We have utilized that. Before our PhD work, this Cortex-based vector rotation was never utilized for image registration. By simply Cortex-based rotation, we have registered both the images. Here the registered image is there, but both the images are registered. Okay. Now what is the advantage? Advantage is that Cortex offers very simple hardware, just add and shifter. So by using simple hardware, not a very bulky hardware, not a very power hungry hardware, by using a very simple hardware, we can achieve image registration. Okay. It is the algorithm of Cortex. Now, to make it even more better, I have changed the Cortex algorithm a little, because we all know that the accuracy of Cortex algorithm depends on the word length. Word length means if each of the values is represented by 8 bits, then Cortex offers a certain accuracy. If it is represented by 16 bits, Cortex offers higher accuracy, but with higher computation time. If it is 8 bit, then the computation time will be half than that of the 16 bit. So the computation time and the bit width are linearly related in case of Cortex. And also the bit width and the accuracy are linearly related. So what we have done, we have changed the Cortex algorithm in this way. Means we have broken down, suppose it is a representation of a angle in binary, and this MSB bits and the LSB bits are segregated. MSB bits are processed by using normal Cortex. LSB bits, which determines a very small portion of the angle. Suppose the angle is 78. The MSB bits will give you up to 64, and from 64 to 78, that 14 value is represented by this low figure, by these LSBs. So these LSBs If we apply approximation, it will not matter a lot. Okay, so what we have done, we have applied approximation by using CSD converter, and by using certain thresholding, we have applied approximation. And by using this approximation, we can get a almost accurate quadratic method. But here the computational load or the computational time varies, that is the latency varies with the logarithm of the bit, not linearly with bit width. It varies with the logarithm of bit width, because you know the concept, the idea was the LSB, the lower significant bits are generally more than the higher significant bits, but the weights of higher significant bits are more. Means the higher significant bits offers much more value, but with less number of bits or with less number of rotation. The lower frequency, sorry, the lower order bits offers many number of rotations. Lower number of bits offers many number of rotation, but for lower value. So what we have done, all these many number of rotation that is realized by using lower order bits, we have approximated that. Then the value will not be altered much more, because it is responsible. The lower order bits are responsible for a very small value. That was the idea. By using the idea, this was the algorithm of quadratic, modified algorithm of quadratic, where the total clock cycle we have taken the relation with the bit width, total number of stage, and the computational load is 2n by 3, log 2n by 3, of the order of log 2n by 3. So the logarithmic relation with respect to the bit width. So we can achieve higher accuracy, but the computational time or the total computation time will not be much more. Okay. So our image registration, the hardware which we have designed, the image registration is achieved with higher accuracy, but with less number of time and less power consumption. Okay. So this is the mapping, means this algorithm, this whole algorithm is mapped into hardware in this way. Means all the topics, means all the operations are segregated: CSD converter, decision maker, then one multiplexer for choosing the operation, iterative contribution, then scaling, then each and every box, black box, are designed here by using normal hardware elements like multiplexer, adder, multiplier. Means ultimately any digital design is nothing but adder, shifter, multiplier. This is the basic blocks, but it is up to you how you simplify the complex algorithm. The complex algorithm may involve the integration, the summation, the logarithm, but you have to simplify it to the basic operation like addition, subtraction, decision making. Okay, so we have simplified that. So up to ultimately adder, subtractor, all these things, and AND gates, all this. So each and every block we have designed, and this is the ultimate hardware for image registration. The registered image means del x and del y gives us the amount of rotation, means amount of shifting that we need to do for each of the coordinate. Means if the coordinate is x and y, that coordinate will be shifted by del x and del y, x plus del x, y plus del y. So del x and del y we have determined. That means the rotation and the shifting parameter we have determined. After that, just the simple numerical operation which we need to perform on the floating image to get it registered with the reference image. So this transform model estimation, that is the estimation of rotation, this portion we have done, where we have focused. Along with that, I have told you there are feature detection, feature matching. All these things are utilized by using standard procedure. Standard feature detection, standard feature mapping. Directly the algorithm is converted into VLSI. It is not optimized. Just this portion, transform model estimation, is optimized. Now, only optimizing this transform model estimation, we have achieved great accuracy. If you can see this conventional quadratic and modified quadratic, the complexity and the hardware complexity is given along with n. Here the time complexity means if the suppose n or the bit length is 12, then the time complexity suppose is 11, and if it is 16 we can increase, then the time complexity is 14. Okay, here it is normalized time complexity, you can say, means just the difference means how much it will increase. But in our here the red portion is our modified quadratic. Here you can see even if we are increasing the number of bits or number of accuracy, increasing number of bits means more accuracy. Even if we have increased the accuracy, the time complexity or total computation time is more or less same. It is not changing. It is logarithmic. That is the achievement. And here hardware complexity is also not exactly in the same linear way it is varying. Okay. It is also linear. Hardware complexity is linear. We have not broken down the hardware complexity to logarithmic. We have only broken down the time complexity from linear to logarithmic. Hardware complexity remains linear, but the slope is less. Means it is increasing very less number of ways, because those LSBs we have uh, incorporated approximation because of this. Here the FPGA utilization details are given for our quartic and for the modified quartic. For the modified quartic, the FPGA utilization and the quartic is also compared with other quartic algorithms. These are the results. Here it comes the more exciting results, that suppose we want to register image if the image size is more. Image size is 255, 256 plus 256. It is okay. If it is 512 plus 512, then the computation time will be more. If it is 1024 to 1024, the complexity normal computation time will be even more, and it is increasing in this way. In this way, normalized computation time means with respect to 256 plus 256. If the computation time for 256 plus 256 is considered as 1, then it is increasing 3.5 times. It is increasing 3.5 times when we go for 256 to 512. It is increasing almost 6.5 times when we increase from 512 to 1024. Okay, but this green color, this blue color, which is our this blue color, which is our own algorithm, coordinates based image registration. There you can see the computational time is not increasing much. It is increasing. Computational time increasing with respect to the image size, but the dependency between image size and computational time, total computational time, is not so rigorous in our case. In our case, coordinate based image registration, computational load will vary along with increasing image size in a very less dependency, in a very by using a very less dependency. Okay? So that is the great achievement. I mean, because the satellite image or the medical image often they are 2048 cross 2048 and more, because 2048 cross 2048 is the minimum required image size for a satellite image. So here the computation time is 12 times than 256 cross 256. But in our case, the computational time is only 1.7 times than 256 plus 256. Why it is so? Because of that coordinate. First of all, we have utilized coordinate, which is very fast, only adder and shifter. So the latency is only the propagation delay of an adder. You can see if it is pipeline, it's only the propagation delay of an adder, the latency, if it is pipeline coordinate. So only the propagation delay of an adder means 4 nanosecond, 2 nanosecond, or 10 nanosecond you can consider. So it is high speed operation, first of all. Secondly, the coordinate we have utilized is not dependent on the image, on the bit width. Here the logarithmic relation is there. So even if we go for highly accurate state, our computational load will not be increased much more. And third point is that here we have utilized the image registration by using only vector overlapping. We are not overlapping each and every pixel by hand. By only single vector overlap, we just determine the parameters through which all the pixels will be overlapped for rigid image registration. So only single or two vector rotation will be sufficient for the whole image registration. But previously, each and every pixels are used to overlap separately. That's why the computational load depends on the image size, because the pixel number is more. But in our case, only single vector rotation is utilized. That's why it is not highly dependent on the image size. It is the experimental setup where our Zinc board is connected with the PC by using MOVA extern, and then the HDMI cables are utilized to send the image from the PC to the Zinc board. Okay. This is the complete experimental setup where we have tested just the transform model estimation step. We have not tested the whole image registration step Only the transform model estimation, that is quartic phase rotation of the image, we have tested. And here are the parameters for MATLAB based and proposed. You can see for MATLAB based operation, the PC power is 77,000. Now you can ask me that PC is doing several tasks. So only for this image registration, the total power, that is 77 watt, is not utilized. Okay, the 77 watt is not utilized, but still it is a very large wattage. But here it is milliwatt. This is in milliwatt range in case of hardware. In case of hardware, the total power supply is milliwatt range. So there is great achievement. Okay. The several other image registration architecture, only two image registration architecture existed before our work. So this is also compared. And that is the main. That is, first of all, for any hardware realization, you need to think of the complexity of the algorithm. And if you find the algorithm too complex, too much complex for it to be the hardware realizable, then you need to simplify it first. Like our image registration, we have simplified it by means of coordinate. We have put the idea of applying coordinate, that is the vector rotation, instead of each and every pixel rotation. So this intuition and idea you need to apply to make the algorithm hardware realizable. After that, you need to simplify the operation by using some simple building block of digital circuits. Then you can easily design an algorithm to hardware. So there are challenges, of course, because algorithms are not so simple. So first of all, you need to simplify it. So that is the main hurdle. After that, you need to optimize the circuit. Means like the coordinate we have utilized. So if we utilize the normal coordinate, then there is a limitation. That is the accuracy and the bit length, that is the computation time. It is linear. But in case of software, we can go for high accuracy, and the computation time will be same because the GPU will process it, and it is highly efficient. GPU is though costly, but it is highly efficient. So if we increase the bit width or accuracy, then the time complexity will not be increased much more in case of GPU or software. That is, it is highly flexible. You can change it. In case of hardware, we have seen that even if we can apply coordinate, but there is a limitation of coordinate. That is the latency. The bit width depends linearly on the latency. If the bit width is more, latency is more, which also incurs the higher computation time, very high computation time. So we cannot achieve high accuracy. So there is a disadvantage. That's why we have modified the coordinate, make the relation in a logarithmic way. Okay, so that is the challenge. You need to compare with respect to software, and software, believe me, is much more efficient than hardware in every aspect. It is flexible. Apart from cost and power, apart from cost and power supply and bulky nature, that is weighty nature, apart from these three, it is excellent. Means it offers flexibility, it offers accuracy, everything. You can program it once, it will give you several years of operation. Everything is fine. But this cost, if you want to optimize the cost and the power consumption for India, third world country like India, you need to go for hardware, and for hardware, every time you need to compare with the software. In software, it can be achieved. In hardware, I need to achieve that. So I need to think that. So this is the challenges and opportunities. In the next, anytime, if I get time, I will show you the multidimensional image processing. In multidimensional image processing in software and hardware, I actually today also I think of showing you by using Python as well as VHDL, but I cannot prepare that. There's Python based image registration and VHDL based image registration, and we can compare the time and accuracy. But I cannot prepare that due to my health. Anyway, I will end this lecture here. If you have any question, you can ask me.
If anyone has any questions, you can unmute yourself and ask at this point. Okay, so sir, I have a couple of questions.
Yes.
So firstly, during your basic lectures, basic slides on images, you mentioned in that slide where you mentioned about Fourier transform.
Yes.
So basically, in 1D signals over time, when we take Fourier transform, we multiply and integrate with complex exponentials.
Yes.
But
Yes.
in
Yes.
images, there is no such concept of time. So how What is the kind of transform that you're using? Can you explain
Fourier
once?
transform is utilized. That means just in Fourier transform, all of we know Fourier transform very well in case of temporal sequence.
Yes.
Means just e to the power j omega t, but here
Yes.
in case of j omega t, here e to the power j omega x plus 1. Means it is the concept of space x and y, two dimensional, so x plus y. So it will be segregated e to the power j omega x plus e to the power j omega y.
So
So here
similarly,
no
the
yes.
concept of frequency as well. So in
Hmm.
time, we note that rate of change of time, if it is fast, the rate of change of signal, it is high frequency. So
Yes,
in the
yes,
images, so we can say the rate of change of pixels, like if the corresponding
yes.
pixels change. So in that
Per
way,
unit, per unit length, rate of
pardon.
change of pixel per unit length. That is space. Instead of per unit time, here per unit length. Everything is converted from time domain, here spatial domain. In case of image.
Okay. So in that way. And one more question I had, when you in that slide where you showed the conversion from RGB to grayscale images, in the numbers
Yes,
which you showed, so you were paying a little more emphasis to the green.
yes,
Yes.
little more emphasis to the
Point
green,
0.6.
because green is that is for human perception. Means this equation, this whole equation is based on the human eye perception. Means in retina, green affects the more.
Okay, so sir, suppose we have an image which contains no green pixel, only red and blue. So only
Uh,
0.41. So 41% of that we can be seen in grayscale.
yes, if there is green pixel is 0, means no
Yes.
green pixel, then 0.59 into g, this portion will be 0.
Yes.
Only red and blue will be combined in case of grayscale image.
So this is for the human perception of the eye.
Yes, yes. Several other formulas can be formulated, but this is more popular. Means because it is determining a grayscale image which is more soothing for human eye. Otherwise, you will get grayscale image also, but that may not be so much soothing. It may be of high contrast, or it may not be perceived clearly. But in this way, point 0.3 R, 0.59 G, 0.11 B, the grayscale image will be more or less similar to the color image, as you can see here.
Yes, these are the questions I had.
Okay, thank you. Okay, so thank you, the Signal Processing Society, for giving me such a chance. It is very much a wonderful experience for me also. Thank you all. Thank you, the Vice President and Vice Chairman and Chairman of the Signal Processing Society also for giving me the chance, specifically Souvik, Santon, Yas, everyone. From my end, heartiest thanks. Thank you all for listening.
Thank you so much, sir. So the one thing, for everyone, please fill up the attendance sheet. I'm addressing to the participants. So I can see that all of you have not filled up the sheet. This is for the sake of the keeping the record. So the link is there in the chat box. So please fill it up. So Tiash, can you provide the concluding note to end the session? Tiash? Okay, I think she's not here. So I will provide the concluding note. So from on behalf of the IEEE Signal Processing Society student branch, I heartily thank Dr. Anirban Chakraborty for accepting our invitation and for providing this wonderful lecture. And it is not very often that we are introduced to very basic concepts from what is an image, going on all the way to the usage of image registration and image fusion. So, sir, you had mentioning some usage of on hands-on material. So you
Yes,
can attach, you can mail that to us, and we can
yes,
distribute it amongst our participants.
okay.
And
Sure, I will do that.
once again, thank you so much, and we will await any other lectures from you in the
Thank
near
you.
future. Thank
Thank
you
you.
everyone for joining.
Thank you.